For centuries, maritime navigation relied on a simple premise. To know your location, you had to see something physical. Navigators determined their heading and bearing by plotting lines against fixed, tangible markers in the water. But physical markers have severe limits. In a heavy squall, visibility drops to zero. Rain and wave clutter can obscure radar returns, making a steel buoy effectively disappear precisely when a bridge team needs it most. To solve this, modern maritime safety has decoupled navigation from purely physical structures. Today, bridge teams rely on the Electronic Chart Display and Information System, or ECDIS. It overlays a continuous data pipeline directly onto the ship's consoles. Surviving in heavily congested waterways requires tapping into this invisible network. Relying on visual lookouts alone is insufficient to guarantee safe transit. This shift operates under a global framework known as e-navigation. It manages the flow of maritime safety data by blending two primary components. The first component is the smart buoy. These are physical aids to navigation anchored in the water, but they are upgraded with active environmental sensors and live transmitters. The second component is the virtual buoy. These are entirely digital objects. They exist as code broadcast to the ship's navigational charts, with zero physical hardware in the ocean. Together, physical sensors and digital agility create a unified, adaptive layer of situational awareness, pushing real-time intelligence straight to the branch. This diagram illustrates a Type 3 AIS AtoN, a fully integrated smart buoy, a multi-sensor array designed to measure the environment. Looking at the top of the mast, we find the atmospheric payload. Instruments like the anemometer and solar radiation sensors collect meteorological data. Below that sits the logic core. Solar panels feed high-capacity batteries, powering the central data logger that processes incoming metrics. Beneath the surface, the mooring line acts as an instrument. Sensors measure water quality, temperature variations, and current profiles. Deploying these massive arrays into the ocean is a major industrial operation, often requiring heavy cranes to manage their immense weight and delicate instruments. Designs vary based on the deployment zone. Some models use a triangular prism shape to maximize solar capture from any angle in open water. Other variants feature a tall pillar-style hull designed to stabilize heavy, top-mounted sensor packages against ocean swells. Modern buoys measure the unseen physical reality, acting as permanent environmental monitoring stations. But gathering the data is only half the problem. How do you push raw telemetry from an isolated floating station to a fast-moving cargo ship? The solution is AIS Message 21. This is a specific digital broadcast protocol reserved exclusively for transmitting aids to navigation data. Locally, the buoy transmits this data over VHF radio frequencies, sending its telemetry directly to any ship within line of sight. Simultaneously, cellular and satellite networks relay the same data back to coastal shore stations and cloud databases for broader distribution. To ensure the data is readable by any vessel, it is formatted using international maritime guidelines like the S100 standard. Because it conforms to these universal standards, the telemetry bypasses scientific research servers entirely and pipes straight into the vessel's navigation displays. This standardized pipeline is the critical link. It transforms isolated scientific measurements into actionable intelligence that bridge teams can use immediately. While smart buoys provide physical data, e-navigation also relies on a digital layer. This chart shows how digital layers manifest on an electronic chart display. Notice the icons labeled Virtual AIS. These signals appear on monitors, but if you look out the window at those exact coordinates, you will only see empty water. This is distinct from synthetic AIS. In a synthetic setup, a physical buoy actually exists at the location, but its presence is digitally reinforced on the chart. Virtual marks do not originate from the ocean. They are generated and broadcast remotely by shore-based authorities. Shore Command manipulates this digital canvas in real time, providing navigation data through an evolving live interface. On the shore side, Vessel Traffic Services, or VTS, manage the flow of ships through congested port approaches. If a sudden hazard appears, like a sunken wreck or a drifting container, dispatching a buoy tender ship to drop a physical marker can take hours or even days. VTS bypasses this delay by using virtual aids to navigation. They can instantly generate a digital marker and drop it over the hazard on every nearby ship's chart. Operators can also use virtual markers to dynamically shift traffic separation lanes. If an area gets too congested, they can redraw the boundaries in real time to ease the flow. Deploying lines of code instead of anchoring tons of steel yields massive cost savings and requires zero physical maintenance. Virtual deployment provides unmatched agility. It turns a sluggish physical response into an instantaneous network-wide safety update. But replacing steel with software introduces new risks. The physical ocean requires hardware resilience, while digital networks are inherently fragile. A physical buoy out in the open water endures relentless daily environmental punishment from the elements. Its digital counterpart on a navigation chart looks pristine, but it relies entirely on unbroken data links. Even smart hardware fails. Heavy marine growth or collision damage can cause a physical buoy to transmit bad data into the network. The digital layer faces a more deliberate threat: AIS spoofing. Hackers can manipulate the broadcast signals. By spoofing data, bad actors alter the coordinates of a virtual mark, making a hazardous reef appear as a safe transit lane directly on a ship's ectus. Blindly trusting digital overlays without independent verification creates a critical single point of failure that can lead to a grounding or collision. Ultimately, the responsibility falls back to the ship's crew, navigating massive vessels through unforgiving conditions. The Nautical Institute maintains a strict legal directive regarding e-navigation. These systems are classified strictly as aids, not replacements for human judgment. Bridge teams are legally required to cross-check digital AIS positions against raw radar sweeps. Navigators must continue verifying their position using visual bearing lines and parallel indexing on the chart to confirm the digital data matches reality. A master mariner's core responsibility involves identifying discrepancies and interpreting data anomalies. Smart networks and virtual buoys deliver highly detailed situational awareness, but the ultimate maritime safety net will always be human intuition, skepticism, and traditional vigilance.